Okay, here's a thought experiment for you. What if a material could actually emit light that has more energy packed into it than the light it first absorbed? Sounds a bit like getting something for nothing, right?
Yeah.
Almost breaks the rules.
It definitely sounds counterintuitive, yeah.
Well, today we're going to plunge into some really cutting-edge research. It's coming out of RIKEN in Japan, and it hints that this seemingly impossible thing might actually be happening.
And happening at the tiniest scales,
Yeah.
right, inside these things called carbon nanotubes.
Exactly. Carbon nanotubes.
It's a fascinating area. You know, most people get photoluminescence, the basics anyway.
Sure, like black lights on fluorescent posters.
Right. You hit them with high-energy UV light, invisible mostly, and they glow. They give off lower-energy visible light.
Energy in, less energy out. Makes sense. Standard stuff.
Totally intuitive. Energy gets lost usually as heat or vibrations.
But what we're digging into today is, well, the opposite. It's called upconversion photoluminescence, UCPL for short.
UCPL.
Imagine shining, say, low-energy infrared light onto something and getting back higher energy visible light.
Wow. Like a tiny light transformer boosting the energy.
Yeah. And you can immediately see the potential, right? Especially for things like solar energy.
Yeah.
Huge implications.
Absolutely massive. So our mission today in this deep dive is really to unpack the how. How does this energy upconversion work in these specific carbon nanotubes?
And we're basing this on that new research you mentioned from RIKEN.
That's right, from physicists there, published recently in Physical Review B. We're going to try and dissect what they found and, what it might mean going forward.
Okay, let's get into the nuts and bolts then. Remind us quickly about standard photoluminescence.
Sure. So light comes in, a photon hits an electron in the material.
Right.
It gives the electron a kick, bumps it up to a higher energy level.
Leaving behind a sort of gap, a hole.
Exactly, a hole. Think of it as the absence of the electron. And this excited electron and the hole, they're sort of linked for a brief moment.
Like two sides of a coin.
Kind of, yeah. That pair is what we call an exciton.
Okay, exciting, got it.
Then usually pretty quickly, the electron falls back into the hole. They recombine.
And that's when the light comes out.
That's when they release that stored energy as a new photon, as light. But crucially, it's typically at a lower energy, a longer wavelength than the light that went in.
Right, like throwing a ball up, it doesn't bounce back quite as high. Some energy loss.
Precisely. Good analogy. There's always some energy lost in that process, usually.
Okay, now let's focus. Single-walled carbon nanotubes. These are, what, like tiny rolled-up sheets of carbon?
Extremely tiny. Imagine a sheet of graphene, just one atom thick, rolled up into a perfect cylinder.
So incredibly thin, almost one-dimensional structure.
Pretty much, yeah. Thinner than a human hair by, well, orders of magnitude. Billions of times thinner.
Wow. And here's the kicker, right? This upconversion, this UCPL. It happens efficiently in these nanotubes, even when they're perfect.
Yes, even when they're essentially free of structural defects or flaws, and that really threw a wrench in the works.
Why? What did people think before?
Well, a lot of the previous explanations for UCPL and nanotubes kind of relied on imperfections. The idea was that these defects acted like little traps, maybe. Places where energy could build up or where excitons could hang around longer, gather more energy somehow before emitting.
Okay, that makes a sort of intuitive sense, too. Flaws doing something useful for once.
Right. But this new research from the RIKEN team, and we should mention the key people, Yuichiro Kato led the work. With Daiichi Kuzawa and Shin Fuji, they found something different.
Okay.
Their work points to a whole different mechanism. It involves something called phonon interaction.
Phonons. Okay. That's probably a new term for many listeners. We know photons are light particles.
Okay.
What are phonons?
Think of phonons as quantized vibrations in the material's atomic lattice, like tiny packets of vibrational energy.
Signaling of the atoms. Heat energy.
Essentially, yeah. The collective vibrations of the atoms in the nanotube structure, these vibrations travel through the material like waves carrying energy.
Okay, vibrations. Phonons. So how do they play into this upconversion?
Well, what the RIKEN team figured out is that that electron hole pair we talked about, it doesn't just get created by the incoming low energy light. It can also gain energy by interacting with these phonons. It can absorb a phonon.
So it gets a double boost.
Yeah.
Energy from the light and energy from a vibration. happening close together.
Exactly, so the incoming photon creates the exciting, and almost simultaneously, a phonon gives it an extra kick of energy.
A vibrational piggyback ride, sort of.
That's a great way to picture it. And this combined energy input pushes the excitant into a special state they call a dark excitant state.
Dark excitant. Okay, dark meaning what? It's hidden.
It means it doesn't readily emit light from that state. It's sort of optically inactive, or at least much less likely to just immediately decay by releasing a photon.
Ah, I see. So it's holding on to that higher energy level for a moment.
Right. It's in this higher dark state. Now, here's the crucial bit. From this dark state, it does lose a little bit of energy, maybe through interacting with another lower energy phonon or something similar.
Okay, so it comes down slightly.
It relaxes a bit, yes, but then it recombines and emits light. And even after losing that little bit of energy, the light it emits still has a net higher energy than the original photon that was absorbed way back at the start.
Wow. Okay, let me see if I've got this. Low energy light comes in, creates an excitant. A phonon vibration gives it an extra boost, pushing it into this temporary dark state. It hangs out there, maybe loses a tiny bit of energy, then bam, emits light that's higher energy than what started the whole process.
You've got it. That's the essence of their proposed mechanism. The phonon provides the crucial extra energy needed for the upconversion.
That's really elegant, actually. So how do they test this? How do you prove phonons are involved?
Well, they did a really clever experiment. They changed the temperature of the nanotubes.
Oh, why temperature?
Because temperature is directly related to the amount of vibration in the material. Higher temperature means more atomic jiggling.
Means more phonons.
Exactly, more phonons bouncing around. So if their model is right, increasing the temperature should make this phonon-assisted upconversion happen more often.
And did it?
It did. They observed that the UCPL effect, the intensity of the upconverted light, got significantly stronger at higher temperatures.
Uh-huh. Direct evidence?
Pretty convincing, yes. As Dr. Cato put it, something like, phonons are more abundant at higher temperatures, enhancing the likelihood of phonon-mediated transitions. It fits the model perfectly.
It makes total sense. More heat, more jiggles, more energy boosts available for the excitants. Okay, so the mechanism seems solid. Let's talk impact. You mentioned solar energy earlier. How could this help?
Right, well, think about sunlight. A really big chunk of the sun's energy that reaches Earth is in the lower energy spectrum, like infrared light.
Stuff our eyes can't see, but it's definitely energy.
Loads of it. But typical solar cells, like silicon ones, aren't very good at converting that low-energy infrared light into electricity. Their band gap is too high.
So that energy is just wasted, turns into heat.
Largely, yes. It's a major limitation on solar cell efficiency. Now imagine if you could have a layer, maybe using these nanotubes or something similar, that absorbs that low-energy infrared light and efficiently upconverts it into higher-energy visible light or near-visible light.
Light that the solar cell can use efficiently.
Precisely. You'd be essentially harvesting sunlight that's currently being missed, converting waste energy into usable energy. It could potentially boost overall solar cell efficiencies quite dramatically.
That would be a game changer. Absolutely. What about the other applications mentioned? Biological imaging.
Yeah, that's another exciting possibility. Sometimes the light you need to use for deep tissue imaging, maybe higher energy light, can actually damage the biological cells you're trying to look at.
Right. Too much energy can be harmful.
But what if you could use lower energy, much safer near-infrared light to penetrate the tissue and have special probes inside, perhaps based on these nanotubes, that absorb this safe light and then emit higher energy, easily detectable, visible light from within the tissue?
So you get the imaging quality without the damaging input energy.
Exactly. It could lead to less invasive, deeper, and maybe more sensitive biological imaging techniques, seeing things we couldn't see before safely.
That's fascinating. And then there was laser cooling. That one sounds really sci-fi. Cooling something down with light.
It does sound odd, doesn't it? But think about the energy balance. If the emitted photon consistently carries away slightly more energy than the absorbed photon.
Where does that extra energy come from?
It has to come from the thermal energy of the material itself, from the phonon bath, those vibrations we talked about.
So each time this upconversion happens, it actually removes a tiny bit of heat energy from the nanotube.
In principle, yes. If you can make the process efficient enough, you could continuously pump it with low-energy light and have it emit higher energy light, effectively extracting thermal energy and cooling the material down.
Wow. Laser cooling, using upconversion.
It's an area the RIKEN team explicitly mentioned they want to explore further. It's not easy, but the physics suggests it's possible.
So potentially not just a way to boost energy, but to remove it selectively. That's quite something. Looking beyond these examples, what else might this open up?
Well, I think the really big deal here is what Dr. Cato emphasized about establishing an intrinsic model.
Right, you've mentioned that. Why is intrinsic the key word?
Because it means this isn't just some random effect happening because of, lucky defects or imperfections in a few specific nanotubes. It suggests that UCPL, via this phonon mechanism, is a fundamental built-in property of these perfect single-walled carbon nanotubes.
Okay, and why is that so important?
Because if it's intrinsic, it means we can potentially design and engineer materials to do this reliably. We're not just hoping for defects.
You can count on it. You can build with it.
Exactly. It moves it from being a curiosity to being a potentially engineerable characteristic. As Dr. Cato said, they hope this opens up possibilities for designing advanced optoelectronic and photonic devices. Think entirely new kinds of sensors, light emitters, maybe even components for quantum technologies, things we probably haven't even conceived of yet.
It really elevates the potential, moving it from chance to design. And it's worth, picturing the team behind this again, Yuichiro Kato, Daichi Kozawa, Shunfuji at the RIKEN Center for Advanced Photonics. Clearly a focused effort yielding some significant insights.
Definitely. Groundbreaking work in understanding these fundamental light-matter interactions at the nanoscale.
Okay, so let's try and wrap this up. The big takeaway. These tiny carbon cylinders, nanotubes, can absorb low-energy light and spit out higher-energy light.
Right. Seemingly breaking the rules, but not really.
Because the trick involves grabbing a little extra energy boost from the material's own vibration. What are phonons?
Yes, that phonon interaction leads to a temporary dark exciton state, which then allows for the emission of upconverted light.
And crucially, this happens even in pristine nanotubes. It's an intrinsic property, not dependent on flaws.
That's the key. Intrinsic, fundamental.
And the potential impact. Well, it spans boosting solar cell efficiency by capturing wasted infrared light.
To enabling safer, deeper biological imaging.
And even the mind-bending idea of laser cooling by removing heat energy.
Plus, opening the door to designing completely new photonic and optoelectronic devices based on this controllable intrinsic effect.
It really makes you wonder, doesn't it? What other, fundamental limits that we assume exist in science might just be waiting for us to understand these subtle nanoscale energy trades, these little interactions.
That's a profound question. Are there other ways energy can be seemingly upgraded or manipulated if we look closely enough?
Yeah, or could this whole upconversion idea inspire completely different ways to think about energy harvesting or light manipulation, things totally outside our current paradigms?
It certainly feels like one of those discoveries that could ripple outwards in unexpected ways.
Absolutely. This research from RIKEN definitely feels like it's cracked open a door onto some genuinely exciting new frontiers for both fundamental science and future technology. Lots to think about there.